Hi, my name is Benet Oriol, and I'm going to be talking about transcription-enriched joint embeddings for spoken descriptions of images and videos, a work I did along with Jordi, Luque, and Ferran Diego from Telefónica Research and Xavier Giro from UPC and BSc. Now, first of all, what are joint embeddings? Joint embeddings are representation spaces trained with the objective of maximizing the similarity of corresponding signals in different modalities. For example, the image of a dog would be mapped by an image model into a similar or close point to where a speech model would map a speech signal of the word dog. Also, they are trained to maximize the distance or minimize the similarity between non-corresponding ones. This is the case of image and speech representations, and this is the baseline from which we depart. From this point, we add a third modality, which is text. The way we train this is very similar from what I just explained, with the difference that instead of only maximizing the similarity between image and speech representation, we simultaneously maximize the similarity of the three modality pairs, so image and speech and text and image. Also, we do the opposite for the non-corresponding ones. The models we use are VGG16 up to Con5, Benet, which is a fully convolutional model for audio, and BERT, which is a transformer. These three models have something in common, which is they don't map the input into a single representation vector. For example, the speech model outputs a feature map, the length of which depends on the length of the input. Same happens with the image models, and something similar happens with the transformer model. The problem with that is that computing the similarity between two representations is not as straightforward as, for example, computing the cosine similarity between two vectors or the Euclidean distance. In order to solve this, we use two steps. First, we compute a match map, and then we compute an overall similarity of this match map. I'm going to give an example with the speech and text similarity. First, we compute what we call the match map, which is the result of computing the inner product between all elements of the feature representations. After that, we compute a scalar similarity score for all the match map. For example, one way would be to do the average of all the match map. But empirically, we found out that it's better to do a maximum in one dimension and the average in another. The data we use is Epic Kitchens. It contains images of kitchen procedures, the spoken narrations of those procedures, and the clean transcriptions of those narrations. Here's an example.
Pick up spoon.
Another example.
Continue breaking up rice.
In order to assess the quality of the embeddings, we use the image retrieval task. Here, we aim at finding the corresponding image given a speech query. Metrics we use are recall at 1, recall at 5, and recall at 10. And we see that we improve performance in the three of them when using text at train time. Note that during evaluation, there is no presence of text. It is only for train. We also do the opposite task, audio retrieval task. And we also get an improvement in the three recalls. We also try it in the places dataset. This is much bigger and contains many more complex utterances. For example, this one.
A small jet taking off from an airport. There are 3 planes and buildings in the background.
And we also improve the performance with respect to the baseline published and our replication of the same experiment. The conclusion is that text can help build more robust speech and image representations and improve the performance of speech and image retrieval, even if text is not present during this task. Thank you very much for your attention.